Hello, today we are still talking about differential equations. These are just not specifically exponential growth or decay. So what I'd like you to do right now is go ahead and read example 1 to yourself. Pause the video to do so, and then I'll start on part A. So pause the video now, please. Part A says we're writing a differential equation. So first of all, I need to have a differential equation. And I know my variables are going to be y and t. My differential equation is going to be dealing with dy dt. So for part A, I know I need to find this information, about dy dt. And it tells me that the rate at which water leaks out is directly proportional to the square root of its depth. Okay, so the rate at which the water leaks out, that is what I have written down so far. And that is equal to, it is directly proportional to is my k times, and then the square root, the square root of the depth. And so the depth is y, and the square root is just square root y. So at this point in part A, we need to find the proportionality constant. So to find the proportionality constant, I need to actually find k. So I'm going to use this last line of information in the example problem. And the last line says, at time t is 0, the depth is 12, and dy dt is negative 3. So I'm going to plug in what I know. So dy dt, I can plug in negative 3, and that's going to be equal to my k times the square root of whatever the depth was. And at this point, when t is 0, the depth is 12. So that's the square root of 12. So from here, I should be able to solve this, and I'm going to get that k is going to be equal to negative 3 divided by the square root of 12. I can also simplify that a little bit and pull the 4 out. So it's the same thing as negative 3 over 2 square root of 3, which is k. And write it however you want. So moving on to part B. Solve the differential equation to find y as a function of t, and then use this information to find the particular solution and identify what kind of function this is. Okay, so for part B, I'm going to scroll down. I'm going to go ahead and just start with my differential equation, and I'm going to use k instead of the actual number, just to make it easier to write. So dy dt is equal to k times the square root of y. So first thing I need to do is separate my variables. So I'm going to multiply by the dt, and I get dy is equal to k square root of y dt, and then I need to divide by the square root of y to get my variables completely separated. And I have dy divided by the square root of y is k dt. At this point, what I'm going to want to do is take the antiderivative of both sides. So I'm going to need to write it in calculus-friendly terms when I do that. So again, I'm going to take the antiderivative of both sides, but calculus-friendly would be my square root of y here is y to the negative 1/2 dy, and then on the other side is k dt. K is a constant. I can pull it out if I want, or I can leave it in. Whichever way it looks more calculus friendly to you is fine. Finding the antiderivative, this is now y raised to the 1/2 divided by 1/2 is equal to kt plus some constant. So now I'm going to write it in non-calculus friendly terms, which is 2 square root of y is equal to kt plus some constant. Now, at this point, I can divide everything by 2 and I can square everything out. But when I want to find the c, this is probably the easiest place to do it. So I'm going to kind of stop here and evaluate what this c is. So I'm moving my paper back up to the top. So part B continued. And so at this point, I have 2 times the square root of y is kt plus c1. So now I'm going to plug in what I know and actually evaluate what c is. So 2 square root of, and the information again that I was given, I've underlined it in green. At time 0, the depth is 12. So my y is 12. I already know my k because I found it before. I'm just going to write it as negative 3 over the square root of 12 times time, and the time when the depth is 12 is time is 0 plus c1. So I now know that this particular c1 is 2 times the square root of 12. Now I should be able to actually write the equation, the particular equation. So when I write this particular equation, I need to solve for y. So I have 2 square root of y is negative 3 divided by the square root of 12 t plus 2 times the square root of 12. Now I'm going to divide everything by 2. Square root of y will then be negative 3 divided by 2 square roots of 12 times t plus the square root of 12. And now what I need to do is actually square both sides. And when I square both sides, I'm just going to put a squared symbol on the outside. I'm not going to work it out. So that is my equation for the depth of the water. Now it also asked, what kind of function is this? Well, if I took that thing and squared it, I would end up with a quadratic. So the function is quadratic. So now we get to move on to part C. Plot the graph of y as a function of t, sketch the graph. So, sorry, the plotting means pick up your calculator and put it in there. And then the sketching is get what you see, write it down. Consider the domain of t in which the function gives a reasonable answer. So what I'd like you to do right now is go ahead, pick up your calculator, enter this function into the calculator. Please be careful when you do that. And then draw a sketch. So please pause the video now to do that. So for part C, we're going to sketch that graph. And it is a parabola. And I believe that it touches the x-axis at 8. And I believe it touches the y-axis at 12. So my function is parabolic in shape, something to that effect. Sorry about that. So this is our basic sketch. And the question is, well, when is this really relevant to our real life situation? Well, this blue is showing the depth of the water. So what it's saying is it started out with a depth of 12 and it went down until after 8 seconds there was a depth of 0, and then the water level went up again. Well, the water level isn't going up again once I have put a hole in this can and the water's leaking out. So that's not part of my relevant domain. So from here to here is not relevant. So my domain that is relevant is for t to be between 8 and 0. So that's my domain. Moving on to part D. Solve algebraically for the time at which the can becomes empty. Compare your answer with the time it would take at the initial rate of negative 3 centimeters per minute. So let's go ahead and look at using this. If we use the initial rate of negative 3 centimeters per second, we would, we're going to use this, that dy dt is negative 3. Then start out with the full can depth is 12 centimeters. So if the water level goes down 3 centimeters every minute, then I'm going to take away 3, I'll be at 9. Take away 3, I'll be at 6. Take away 3, I'll be at 3. Take away 3, I'll be at 0. So I'm going to take away that many, which means it's 3 centimeters every minute. So it's 4 minutes the can is empty. Okay, so that's again using this initial rate of negative 3 centimeters per minute. I could have easily just taken 12 and divided by 3, and would give me the same thing. So let's go ahead and actually do this algebraically now. So I want to know when the depth is 0 And that is when I have my function, negative 3 over the square root of 12 times t plus the square root of 12 quantity squared. And I'm solving for t. So I'll go ahead and I square root both sides, and I still end up with this. And then I'm going to isolate the variable. I'm going to bring the 3 square root of 12t to the left. And then I'm going to solve for t by multiplying both sides by square root of 12 over 3. Oh, I lost a 2 somewhere. Oh, sugar. So sorry. Okay, when I wrote my function right here in my first step, I forgot the 2 that's right here, 2 that's right here, 2 that's right here, 2 that's right here. So I am very sorry about that. So I really have 12 times 2 on the top divided by 3, which is going to be 8 minutes. Sorry, no, by looking at the graph, it should take 8 minutes. So we have now finished this problem, although I made a mistake in it. I apologize. What I'd like to do now is move on to the next problem. However, for the next problem, you are probably going to need another piece of paper. So 2 things. What I want you to do is get a piece of paper and read the example 2. I will pick up with part A. So go ahead and pause the video now to get paper and read example 2. Okay, so we're on part A, and what does L equal in terms of W? So finding L, the leakage rate L is directly proportional to the amount of water present in the lake. Okay, so I just have a direct variation, which means my L is directly proportional to the amount of water in the lake. Now I'm actually going to pause for a minute and start writing down some variables because I think we're going to have a lot. So already I don't know what these things are. So L is the leakage rate. So this is the rate. I'm going to start with the word rate so I know it's a rate of change that the water leaves. And the units for that is feet cubed per hour. The next thing I know is W. W represents the water in the lake. And the units for that are cubic feet. Next thing I know is F. And if you had read that, F is the water starts flowing in at a rate of F. So F is another rate that water comes in. And that is in feet cubed per hour again. And then I have my last unit is my time unit, and that is T. And that is time. Is this in minutes, hours, days? Looks to be hours. Hold on, I'm going to scroll up. Oh, time equals 0 days. Excuse me. Well, I think I did this in terms of hours. I will be honest with you, because I went on and when I read the rest of the questions, part C has a leakage equation is 0.04 per hour. And again, in part D, it talks about hours. So I'm actually, and then part A talks about hours. So we're going to say time is in hours. That's what I'm going to do. So if we need to convert anything into days, we can, but it looks like a lot of our information is actually in hours. So talking about part A still. Sorry, I just wanted to get our variables out of the way. What does L equal in terms of W? Okay, did that, directly proportional to W. Write a differential equation that expresses dW dt, dW dt in terms of F, W, and T. Well, dW dt, scrolling back up, the instantaneous rate of change of W, so this right here is dW dt is equal to F minus L. So I can put that down as F minus L. However, in the directions for part A, I could not use L. I'm going to erase what I had written. I could only use F, W, and T, which point I need to rewrite this as dW dt is going to be F minus KW. So I don't have a T in there, but that's fine. Part B, solve for W in terms of T using the initial condition W equals 0 when T equals 0, at which point I need to separate my variables and do my antiderivative. So what I'd like you to do right now is I want you to separate the variables and find the antiderivative and then press play again. I want to make sure that you have the right antiderivative before you go forward and find your C value. So please pause the video now. So this is what I got when I separated my variables and found my antiderivative. Negative 1 over k natural log of the absolute value of f minus kw equals t plus a constant c1. So what I'm going to do now is I'm going to try and solve for w, which is ultimately what I want to solve for. And finding c, I think, is going to be easier once we have our function in terms of w. So in this one, I'm going to keep working. So k is a constant. I'm going to go ahead and multiply through by negative k, so I don't have that there anymore. And that will leave me with natural log of f minus kw is equal to negative kt plus some other constant. That's c1 times negative k, but I don't care what c1 is. I only care ultimately about the final constant. So now what I need to do is I need to um, get this w out of my natural log. So the only way that I can do that is take e to the raise on both sides. So I'm going to raise e to the left side and e to the entire right side as well. So once I have done that, I now have f minus kw is equal to some other constant times e to the negative kt. So at this point, F minus Kw, F is the rate the water flows in, K is a constant, W is the amount of water that I have in the lake, but this can't be a negative entity, if that makes sense. So this is going to remain positive. So F minus Kw is going to be C e to the negative Kt. So from here, what I need to do is actually get W by itself. So I'm going to subtract the F and divide by the K. So when I do that, I have this thing minus F, and I'm dividing by a negative K. I'm just going to go ahead and multiply by a negative 1 over K. So if that didn't make sense, take another step to work yours out and see if you get what I got. So now what we need to do for part B, we're still working on this, is we need to solve for C. So we need to find some information. So scrolling back up, we have the initial condition that W equals 0 when T is equal to 0. So I'm going to plug that information in. So W is 0 when T is 0. So now what I need to do is actually solve for C. So I multiply both sides by K, negative K, and C is the same as F. So now I can write my equation is negative 1 over K times F e to the negative kt minus f. And if I wanted to simplify that, I can go ahead and take that f out. You'll see that they're both f's. The other thing I can do is distribute the negative in. So to make this a little more simple, I'm going to distribute my negative into both of these, which is going to reverse them. And I'm going to factor out an f as a GCF. So my f comes out, my k is outside, and I have 1 minus e to the negative kt. So again, if you don't get that, pause it for a minute, see if you can figure out what I was doing when. Moving on to part C. Water is known to be flowing in at 5,000 cubic feet per hour. Based on geological considerations, proportionality constant in the leakage equation assumed to be 0.04 per hour. Write the equation W substituting these quantities. Okay, so now we're just plugging stuff in to the equation that we had. So I'm going to take this equation that we have down here and I'm going to rewrite it and then plug stuff in. So for part C, I start by rewriting. This is where we were, and now I'm just going to plug stuff in. So I know that my F is 5,000 divided by my K, which is 0.04, 1 minus e to the negative 0.04 t. And I can simplify that if I wanted to, or I can leave it alone. This number is 125,000. So that's part C. There's our equation. Now for part D, what it wants is to find a couple of things. So at time is 10 hours, how much water is in the lake, how much water has flowed in, and how much water has flowed out. At time is 20 hours, the amount of water in the lake, how much water has flowed in, how much water has leaked out, and the same for 30. So I would go ahead and do this in a table. I'm not going to pull the calculator up right now, but that's what I would do. So grab your calculator. And in our table, what we need is our W. So in Y1, I would put what our W is, which is right above. In Y2, I could probably figure that one out. But you could do Y2 is going to be the amount of water in, and the water comes in at 5,000 cubic feet per hour. I believe that's the constant that we were given. So it's going to be 5,000 times T, which we're actually using X. And then for Y3, the amount out would be the difference between the two. So that would be Y1 minus Y2. So I would go ahead and put all those into your calculator and go into a table to find those values. I'm going to go ahead and write them down. But go ahead, figure that all out and write it down, and pause the video to do that, please. When you've got your table completed and written down, turn it back on and I'll have the answers up. So pause the video now, please. Here are the values that I got. Please pause the video so you can check your answers now. Pause the video now, please. Okay, moving on to part E. Question part E is, when will the lake have 100,000 cubic feet of water? So for part E, we should be able to deal with this. We want to know when the water is 100,000. That's a parenthesis there. So I can set it up like this. I'm going to go ahead and work it through algebraically without using my calculator, although you could use your graphing calculator to solve it. I'm going to divide by 125,000. And then I'm going to go ahead and subtract the 1. Now both the left side and the right side are negative, so I'm going to multiply both sides by a 1. I have an e, which means I need to take the natural log of both sides in order to work this out. So just by taking the natural log of both sides, I have pulled that negative 0.04 t out, and then I'm going to divide. So t is going to be the natural log of 0.2 divided by negative 0.04. If you pick up your calculator, that should give you 40.2359 hours. Moving on to part F. Find the limit of W as t approaches infinity, and what is the real world meaning of this number. So, moving on to another piece of paper, sorry, underneath my table. So we have part F. So I'm taking the limit as t approaches infinity of my W So let's see what's going on here as t goes towards infinity. As t is going towards infinity, this is becoming a negative, really, really big number. So just to kind of show what's going on, that's not an equal sign, by the way. So I have e raised to a negative really big number. So it's 1 over e to the 0.04t. That negative exponent just puts it in the bottom. So this thing in the bottom here is trying its best to become a really big number. And 1 over a really big number is trying its best to become 0. So this is what we're trying to get to. And when you work that out, it is trying to become 125,000. So it's 125,000. And what does this mean in real life? Well, that's probably what the lake will eventually hold. So it's the cubic feet the lake will eventually hold. We also call that the carrying capacity of the lake. That's the most that the lake will actually hold. Moving on to G, I'm not going to go back, but G says we're trying to draw a graph of this. So by drawing a graph of this, and it says we need to clearly show the asymptote. I've got this function, it's an exponential k, it's upside down, it's going to go like this, and my asymptote here is what my y value is trying to eventually be, and this asymptote is 125,000. Part H. Part H is the lake starts filling with water. The actual amount of water at time equals 10 is exactly 40,000 cubic feet. The flow rate is still 5,000 cubic feet per hour as predicted, and use this information to find a more precise value of the leakage constant K. So we're trying to find K, and we're trying to do a better job. So we're going to say F is 5,000, and we know that W is 40,000, and this was at time is 10 hours. So I'm going to plug all this in. So 40,000 goes in for my W, 125,000. Oh, sorry, we're trying to find that. It's going to be F divided by K times 1 minus E to the negative KT. Sorry, back up a minute. That's the equation I'm starting with because I'm actually trying to find K. I apologize. I started with the F and K that we had before. So I now have 40,000 is equal to 5,000 divided by K times 1 minus E to the negative K times 10, because we're at time 10, negative 10K. Now at this point, what I would like to do is multiply both sides by K, and then eventually I take the natural log to get the the exponent out of the E. If I do that, then I'm going to have my variable, K, will be inside of a natural log. So my point is, this is impossible to solve without using your graphing calculator. Okay, us mortals can't do it. So you're going to use your graphing calculator. So put y1 can be 40,000, y2 can be 5,000 divided by x times 1 minus e, the negative 10x, and then do an intersect. And when you solve that, you get that the actual value for k is 0.04642. I apologize for the length of this video, but I hope you have a better understanding of differential equations and taking word problems and solving them using the mathematics at hand. I hope you have a wonderful evening.